So this is Chapter 3, Chemical Equations. And classification of reactions. There's a number of points that I need to talk to you about in relationship to what the reaction means in its context. Many of the points are familiar to you, but there'll be some that are not so familiar. As you know, the chemical equation is a shorthand method for defining chemical process or physical process. In an example of this, if we start out with hydrogen gas and oxygen gas, we can, through process, make water. And you can make water gas, which can be condensed into H2O as a liquid. Now, the issue here is, oops, I'm going to put it right there. I'll put it right here. We'll explain that in the future. The listing from the hydrogen, oxygen to the H2O in the gas phase is a chemical process. Because the products are totally different than the reactants in physical and chemical properties. I think you can appreciate a gas phase hydrogen or gas phase oxygen in liquid water. And the general differential between the two is easy to note. The H2O gas going to water is a physical process. It is a change in state, i.e. solid to liquid, liquid to solid, back and forth, whatever. And you do not change the chemistry of the molecule itself. You retain that structural characteristics of the water, even though it's in a different physical phase. When we write out chemical equations, the preferred format is to list the reactants first, a yield, an arrow which defines a yield, say that reactants will produce products. In that way. Now, there are some characteristics of chemical reactions and the notations that you use in these that you have to keep in mind. Number one is the chemical equation conforms to the law of conservation of matter. This means certainly that the sum of the masses of the reactants must equal the sum of the masses of the products. And we recognize that in our chemistry courses and science courses, balancing the chemical equation. Now, there are a couple of balancing processes that you will be shown today. One, general inspection, and 2, an oxidation reduction procedure. Or just simply balancing oxidation reduction equations like that. And both, of course, require practice, and that's why I've given you some worksheets, and we'll go through some of the balancing procedures that are listed to emphasize some of these, and especially the oxidation reduction. It requires that you learn some rules of how to apply an order of solving that balance as you go through trying to put coefficients and what have you into the reaction. When a reaction is written, or as written, as it's given, it's assumed to be in standard state. A molecular reaction, let's put it that way, we'll emphasize. .0 Celsius or 273 Kelvin and 1 atmosphere pressure or 760 millimeters of mercury. We'll emphasize those when we get to gas laws in more detail. But when you see a reaction written in a worksheet as say these and say it's balanced, once after you balance it, you do not have to have a notation or a sidebar to know what its assumed the conditions are, because that has a lot to do with of course, the gas phase components of the reaction. So you have a place to start. All of the chemical community and scientific community accepts that fundamental preface or premise in terms of saying the chemical molecular reactions, when balanced, are assumed to be at 0 degrees and 1 atmosphere, or associated dimensions of variables, state variables. When a reaction is written, a molecular reaction is written, its components are written in basic standard state and balanced from the basic standard state. And what that means is a little different than assuming standard state 0 degrees and 273 and basic standard state of compounds and elements. So the notation here is molecular equations must be written such that the components of the equation are given in basic, I'll move that down to emphasize that, in basic standard state. Now, basic or standard state in gas laws, 0 and 1 atmosphere, is different than the basic standard state conditions. This is called thermodynamic conditions. and this is 25 degrees Celsius and 1 atmosphere. Just giving you the fundamental facts on the issue. Now, you won't have to use this number at when working initially with the equations, but you will have to use the 0 degrees and 1 atmosphere issue, and I'll cover that at the appropriate time. Now, back to this phrase. Substances in basic standard state is the topic. Typically, they are found in the appendix of your college textbook. Basic standard state conditions, or state values, are typically in text appendix. So in the textbook, you go to the appendices of that textbook, and you'll find a table of listing many compounds in basic standard state. They're called thermodynamic standard states, if I can find it. So Appendix C in Ebbing's text says here is thermodynamic quantities for substances and ions at 25 degrees C, and you can throw in 1 atmosphere into that, okay? So you have certain symbologies up here that we will explain at the appropriate time, but you have this alphabetized listing of formulas for many compounds. You can see over here, just goes on and on and on, and they're categorized relative to the central element that makes up that compound. Now, when writing a chemical formula equation in molecular form, apply standard state forms equations to molecular equations. Now, here's what I'm really getting to in trying to explain this idea in here. We have basic standard states of elements and basic standard states of compounds and substances. And you need to understand intuitively the difference between those two in order to go forward and understand how these thermodynamic issues and energy issues are applied to the chemical equation. Given, for example, let's go back to, I'll use this equation, 3H2 gas plus N2 gas goes to 2NH3 ammonia gas. So let's jot that down in there. Now that is the correct form, and it is balanced for that process. The question is, why can't I simply write 2N plus 3H gives me NH3? Why is this incorrect? Because the substances involved in the reaction are not in basic standard state. you have to list hydrogen as an H2. You have to list nitrogen as an N2, and you have to list ammonia as an NH3. Now, they're ammonia gas and ammonia liquids, and depending on the process, you pick the one that best fits the issue. So, looking in the table under hydrogen, we see, come down in here and we find where is my hydrogen? Should have H2. There it is. Right there. You see that? Now, guys, watch this if you're not familiar with this, because this is going to show up on a lot of stuff in the future. But what you're looking at is I have to use the H2. Well, I've lost it. Yeah, there we go. In this form right here. How do I know that that is the form of the hydrogen that I'm supposed to use? Because over here there's a 0 under this symbology that's up the top here. See the delta HF? That's called the standard heat of formation. When the standard heat of formation equals 0 for elements only, that's the form you put into a chemical equation. So, H2 in gas form is listed under delta HF 0 equals little superscript 0 is equal to 0, and it'll show kilojoules per mole. Well, all elements in basic standard state that are in basic standard, now you have elements that are not necessarily by themselves, but not necessarily in basic standard state. I'll show you that in a second. But if this is a 0 next under this symbology, then that will be a basic standard state for that substance, for that element. Nitrogen. Why is nitrogen listed as an N2 in this equation? Because it is in basic standard state. So we go back to our table, zoom in, under nitrogen, and you see where it's under 0, and it's in this first column, and that's a delta HF column. So all of the nitrogens, if I put them in other kind of equations, have to be listed as an N2 gas, like that. Well, what about ammonia in this? Well, how many forms of ammonia do you think there are in the universe? Maybe a solid ammonia, or liquid ammonia, or gas phase ammonia if under the right conditions. But ammonia is still NH3. So when you look up ammonia, it doesn't matter. You got to use NH3. There's only one of them floating around. Does that make sense? A little bit? Now stay with me now. Let's go back down to the nitrogen collection here for a second. And look for ammonia, see if we can find it. And what do you see? The basic standard state. Well, this is 25 degrees in one atmosphere, and that is the physical conditions necessary for a gas phase ammonia. Well, you don't see a lot of them in here. You just see one in here. But it has a number over here that the elements do not. The elements, if you go back up here and look at N2, it's always a 0 or any other element in basic standard state. So you can go through this table in column 1, and if you see, every time you see a 0, it's a basic standard state. And that's the form you have to use in the molecular equation. Now, there are ionic equations and structural equations in which you don't conform to this, but those are application. But in a collective sense where you're trying to write molecular equations for this course, you will need to have this table or have indicators under your problems. You'll be able to look it up. You can go online and type in standard heats of formation for substances, and it'll give you 1,000 citations on tables just like this. And so you'll be able to look it up and see what form to use. Now, you notice in this, as I've written it, let me show you one other bromine. I'm going to go over here to bromine. Just to make a point here. Here's bromine. Look at you got 1, 2, 3, 4, 5 bromines by themselves. But only one is in basic standard state. And that one is the Br2L liquid flame. That's the only one on there. So when I say only elements in basic standard state have 0 standard heats of formation, but compounds always have a value out here, as well as non-standard state forms of an element. Those are non-standard state, and those have specific applications. So if you have a molecular equation that uses a specific application, then you would choose whatever you need, but it'll have a number associated with it. Now that's another story that we will cover in due time in the proper place. But hopefully you're beginning to see that when you write out a chemical equation written out in molecular form, where the sum of charges equals 0. Remember, when you write out a formula, one of the rules is the sum of charges must equal 0. Unless it's a polyion, it must equal the polyion form, the net charge. But we're just talking about neutral compounds right now. So at any rate, the idea is, how do you know that's what I'm supposed to put into the equation? It's in standard form. There's only one of them that ammonias, in the same way with other compounds. They're not a bunch of waters. Water is always H2O. Yeah? Okay, and carbonates, bicarbonates, and all the thousands of compounds, there's only one of them. Now, elements can exist in other forms, ions and what have you, but there's only one form in each element that is classified as basic standard state of that element. Here's a little trick that I try to show my students. Delta HF, I wanted to put that equals 0 kilojoules per mole. These are referred to as diatomic molecular nitrogen or molecular hydrogen, because they're 2 or more elements chemically combined. That's the definition of a compound. The question is, how many diatomics, without looking in the thermodynamic tables, are in basic standard state? Anybody know? Yes.
Is it
How many?
Is it 10? 10
Subtract
elements?
3.
7?
7.
That's close.
Actually, there's 7. And they're very easy to find. On the periodic table, this is a trick, guys, so enjoy it. Hydrogen, we have already seen that one. You just got to remember that one. That's the hard one right there. But the others in this table that are diatomic are right here. What's the shape of that figure? It's a 7. You see that? So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all diatomics, but you just got to remember hydrogen. Can y'all handle that? Yes.
So why isn't AT diatomic?
Which one?
AT? I think it's AT.
Number 18?
AT. Below the 7. I don't
Which
know
one?
exactly which one it is.
I didn't understand.
Look below the 7 that you drew. That element, why isn't that one not diatomic?
Wait a minute. Our next topic is balancing chemical equations. Some are relatively easy to balance, and some are not necessarily that easy to balance. And so you should have the handout I gave you a little while ago. Looks like this, as well as some attachments. Third or fourth page down, you will see something, a little set of rules. And yeah, you got to learn rules, and that's awful. But once you get into them and learn how to deal with them, hopefully I can show you effectively. They're not so bad. Okay. So there are 2 accepted methods of balancing equations. Of course, you got to conform to the law of conservation of matter. Some of the mass of reactants must equal some of the mass of the products. I think everybody understands that that idea. Now, a couple of little factoids. If I have an equation, and we've worn this one out, but it's very useful in its context. One thing that is in a chemical equation before balancing is the subscripts. You cannot change subscripts unless you are predicting the outcome of a reaction, but assuming you have both sides of the equation, reactants and products. Because the 2's and subscripts and whatever you write, define that substance. You don't just arbitrarily put down O for oxygen, because that's not what comes out of that reaction. That reaction delivers O2. Okay? And water formation, when it occurs, comes from H2 and O2. And the results is H2O. Not HOH or HHO or just whatever. It has 2 hydrogens and 1 oxygen. So the form of water is given, the other reactants and products in the compound, in the reaction equation are given. You can't change those. If you change the subscript, you change the substance. I think that's obvious. So how do I change the number? So if I look at this, I got 1 oxygen and 2 oxygen. Well, the only way you can change the numbers of elements within a given equation to balance it is using coefficients, as you would expect. All right, how do you use those? Well, there are 2 ways. By inspection and by applying rules of oxidation reduction reactions. I should put it in here for balancing. That set of rules I showed you a few minutes ago, that page of rules and things that we gave you. So, of course, we want to look at the ones on inspection, and some of them are kind of tedious and require a little bit of work, and some of them will go fairly smoothly. Like in the one for water, we need to increase the number of oxygen, so that would require putting a 2. That's the only way you can increase the number of oxygens. Well, when you do, it also applies to everything behind the coefficient, which is hydrogen. So now I have 4 hydrogens, so I can come over here and put a 2. So that's inspection. And some equations will balance out very quickly, like this. And this one, you have a 3 against a 2. Well, how do you manage that? Well, one thing you can do is swap coefficients like that. And now I have the 6 and 6, but that kind of tangles up the KCl. Well, I can balance that as kind of collectively, just simply put a 2 in there, and that takes care of that. Now, that takes just a little intuitive experience. That's all it does. And so that's why I've given a collection of equations to balance or try to balance. And so you can see this Arminian here. And so I'm going to pick to a 3, and then we'll just use these as a starting point. Then you do the rest of them. If you run into problems, certainly get in touch with me. So you've already seen this one. So we need a 3 against a 2, and I just showed you can swap the coefficients and go there, and that's already in a diatomic format. So you can throw the coefficients in. And if you look at it, you have 2 nitrogens over here, 6 hydrogens, and then over here 2 nitrogens and 6 hydrogens. So that would constitute balanced in that ratios. And those are called reaction ratios or interactive ratios. You always have an N1, N2 interacting with 3 H2s to produce 2 ammonias. And that will come important in next chapter. Here's that KClO3 we just did. There's also, just to remind you, in the polyion, remember talked about an analogous series where you have K, you can substitute the halogens and they will generate the same types of compounds, KBr and KIs plus O oxys like that. And that context. Anyway, we would need a 2 in front of each one of these. And 2. Like that. So those are just some things that pop up on these inspection type. So how do you balance something with a whole lot of the letters in it like that? Balance it by polyion groups. So what we're looking at here is one sulfate right here against 3 sulfates over here. This has got to be given because the aluminum sulfate has this formula. So if I have 3 over here, I can increase those by simply going here, because what I'm doing is I'm increasing all of that polyion. And then so that moves this to 6 potassiums. And so to balance my potassiums, I can put a 6 in here. And so if I come in here with 2, I'm 2 and 3 is 6. Like that. But when you have an equation that looks like this that swaps the ions, and that's called a metathesis reaction. You use the particles and balance the polyions, left against the right, like that. It works better that way. Let's see, there's another one. Most of them you're probably very familiar with, and here's another metathesis. Here's iron chloride, same idea. going to iron hydroxide. And sodium chloride. Like that. So look at the polyions in the collection and try to balance those first. See, what you're looking at is 3 hydroxides on the left and right, so put your 3 in front of the sodium hydroxide. And use your sodium here, and then balance it, make that a 3. So that would affect the chloride here. Then now you got 3 chlorides, 1 fluoride, and usually 1 or 2 coefficient entries in these metatheses will balance the entire equation. They are not that difficult to deal with. Now, there are some that can get gnarly, but for the most part, they're pretty straight up. If you know how to balance them or start to use the groupings of the polyions, left and right, reactant side and the product side. Let's see what else we got here. Now, I'm just spot checking these. Oh, sometimes you can use fractions in equations to balance them. They're not, let me make, now hold that comment. Combustion reactions is when a substance interacts with oxygen. Now, the ones that you will be working mostly with are hydrocarbons. So a hydrocarbon is a compound that consists only of hydrogen, carbon, or oxygen, or nitrogen, or something of that nature. But this is hydrogen and oxygen only. Man, when you write it as a plus O2. So that indicates that hydrocarbon compound, whatever it is, plus O2, gives always, did you hear that? Always CO2 and water. And you can list that as a solid, not solid, a liquid or a gas, if you, however you want to list it on that end. So it's always CO2, carbon dioxide, and water when a hydrocarbon is burned. And that's a combustion reaction. A simple one would be CH4 methane. That's the simplest hydrocarbon. And reacting that with O2 gas always produces CO2 gas and H2O. We'll list it as a liquid here. Now balance that. Well, what I recommend in many, not just this kind, but when you have a reaction like this to balance, if an element, whether it's standard state or not, leave it last. If it's by itself, wait till last to balance that particular one. Because all you have to do is put a coefficient that will make it balance and force the balance. For example, carbon is 1 and 1, but you got 4 hydrogens, so you have to increase your hydrogens by putting a coefficient here. But what does that do to the oxygens? You got 2 and 2 is 4, but you got 2 over here. So by saving this to last, I immediately see that 2 of those will balance that. Let's see if I can C5H12. What is it going to produce when it undergoes combustion? O2, CO2, and water. That's what I'm trying to tell you. This is a no-brainer. When you see a hydrocarbon and oxygen, it's CO2 plus H2O. Now balance the carbons and hydrogens and then save the O2 to last in the balance. So you have 5, so I'm going to put a 5 right there. So now I got those balance, carbons balance. Now I have 12 hydrogens, so what do I need to do here? I got, put us 2 and 6, 12. Now I got my hydrogens balanced, but the oxygens are 2 and 5 is 10, 11, 12, 13, 14, 15, 16. Well, this one didn't work out like I'd hoped it would, but all I have to do is put an 8 in there. See if I can come up with a better one. That's how about C4H10. And make that an O2, CO2 and H2O. Save O2 to last in the balance, so I'll need 2 there. And I'm going to do hydrogen. I need a 2 to 5 is 10. 2 to 5 is 10. Well, that one won't work either. Sometimes you wind up with a fraction, like if you have 5 over here and over here, so you can go 5 halves, something of that nature, and then multiply through by 2 to remove the fractions. That's legal, because it does, in fact, balance the equation. I just can't think of a hydrocarbon right now. I can play with it and eventually find one.
It's number 9.
Which one?
Number 9.
Number 9.
I think it's one that you're talking
In the collection?
Yeah, in the
Oh, okay.
Like,
Let me, all
number
right.
9.
Yeah. Gotta get that one finished. Let's see, let me be sure. 4, let's see, let me finish this one. So C4, that's 4 carbons, 10, 2 to 5 is 10, 2 to 4 is 8, 9, 10, 11, 12, 13. Here we go. It was correct. So 13 has. Well, then this is the same as 2C4H10 plus 13O2 goes to 8 CO2s plus 10 H2Os. So I can times 2 and get everything in kind of whole numbers right there. Now, yeah, if number 9 comes up with a fraction, fine, use it. But save the oxygen just last, and you just use a fraction there. I think everybody, y'all see what I'm saying? Okay. One other notation here on this that I forgot to mention. When we say a reaction is in basic standard state or in standard state, there's one other thing that qualifies it. The coefficients are in the smallest whole number ratio. A standard equation or for a standard state equation, coefficients must be in smallest whole number ratio. Not just combustion reactions, all of them. Go back to the ammonia production. You can't reduce the coefficients any further than they are now. They have to be in the smallest whole number ratios, and of course you can use fractions, but that's not the standard equation. Now I can use multiples of this by multiplying by 2. I get 6H2 gas plus 2N2 gas goes to 4NH3 gas. However, this is not in standard form, i.e. not at 0 degrees Celsius in 1 atmosphere. You just can't. It might be, yeah, right, but it's not of the form that you can say that. That's the point. Yes. In the scientific community, when we say standard form, smallest whole number ratios as written is in 0 degrees in 1 atmosphere. Then you can go on and work all the problems based on that. But if the coefficients do not match that, yeah, it might be, but it's still not a standard state form. Okay.